In step 6, we're going to actually continue kind of building upon what we did in unit 1, talking about different features of functions, the domain, the range, the intercepts, the continuity, symmetry, where is it decreasing and increasing, the end behavior, and so on. The only difference in step 6 is we're looking at some different functions. So let's start. Here is a quick review that most of you should probably remember from Algebra 2, that if the degree of our power function is even, then both ends point in the same direction. Just like you see here, both ends are pointing up, both ends are pointing down. If the degree is odd, like a cubic function, then one end points down and the other points up. Then we look at the leading coefficient. If it's positive, and it's even, they point up. If it's negative and even, they point down. With odd, it gets a little more challenging, so I tell students, pretend that this graph is actually a pipe cleaner and imagine stretching the ends straight away from each other so that it just makes a straight line. This line would have a positive slope. This line would have a negative slope. So that's how you can kind of remember that. All right, let's try the first one. Now, with this video, I strongly encourage you, when I suggest that you pause the video and try it yourself, really do that, because that's a great way to make sure that this is making sense. The video itself will probably give you one example and then one for you to try. So for the first one, they ask us to graph it, and you can see that the domain goes to the left forever and to the right forever. It has a range of 0 to infinity. The x-intercept and the y-intercept is 0. As x goes to the left, the graph goes up. As x goes to the right, the graph goes up. It is continuous everywhere. It is decreasing from negative infinity to 0 and increasing from 0 to infinity. You can look through example B also. Let's try example 1A. We're going to list all of these features for 1A. So first up, we need the domain. We're going to need the range. And you can put this function straight into Desmos. Let me actually open up Desmos so that you can see that. Okay, here you can see I've typed in that function. I'm going to minimize that list. You can see what this graph looks like. So clearly it goes to the left and to the right forever. In fact, if you zoom out, you can see that even more clearly. Negative infinity to positive infinity. The range, however, the lowest it goes is 0. And there is graph at 0. So it goes from 0 to infinity. You can see from the point 0, 0 that both intercepts are 0. The end behavior is actually going to be the same end behavior that we had right up here for part A. You can see how similar these functions actually look when you graph them. So our end behavior, we write the limit as x approaches negative infinity of f of x is infinity. And then we write the limit as x approaches positive infinity of f of x is also infinity. We can see that this function appears to be continuous everywhere. So we would say it is continuous on the interval negative infinity to infinity. And finally, where is it increasing and decreasing? It is increasing from 0 to infinity, and it is decreasing from negative infinity to 0. Pause the video and try 1B. All right, hopefully you got those same answers. Let's go ahead and take a look now at functions with negative exponents. So for this first one, type it in here. it is 3x to the negative 2. Now we could also type 3 over x squared. In fact, I'll show you that. 3 over x squared. It's the same thing. Blue function, red function, blue function, red function. Doesn't matter which way you type it. It means the same thing. Okay, so let's talk about the domain here. The domain, it appears that there is graph except at 0, which makes sense because this function, if this is really 3 over x squared, we have a fraction, and that cannot be 0. So we know that we're going to go from negative infinity to positive infinity, but we're going to have to break it at 0 because x cannot equal 0. Additionally, you can trace on this graph, you can see that it does get smaller and smaller and smaller and smaller, but it never turns negative. So our range is from 0 to infinity. It never equals 0. There are no x and y intercepts. As the graph goes to the left, it approaches 0. As the graph goes to the right, y approaches 0. It has infinite discontinuity. At x equals 0. But it would be continuous on its domain. It is increasing from negative infinity to 0, and it is decreasing from 0 to positive infinity. Pause the video and try the second one. My apologies, I just realized that that function was chopped off from your notes. There it is, negative 3/4 x to the negative 5th. Try that one. Next, we're going to go ahead and take a look at rational exponents. So we can rewrite rational exponents with a radical. This just means the index is 2 and the power is 5. So that means the same thing. So again, if you're typing this as a function in Desmos, you can type x to the 5/2, or you could type the square root of x to the 5th. You get the same function. Purple, green, purple, green. They're the same function. All right, so on this one, when we're trying to figure out what this graph looks like, what's the domain, what's the range, again, even without looking at the graph, we know that what's under the radical here, this cannot be negative because we have an even index, so it has to be greater than 0. So we know that the domain has to be greater than or equal to 0. And similarly, the range is also greater than or equal to 0. X and y intercepts would be 0, 0 again. And behavior. Well, this only has one end. This is the starting point, but this is the end we're talking about. Notice on our other graphs, we had a left end and a right end. We had a left end and a right end. But down here, we only have a right end. So we're only looking at the end behavior as x goes to infinity. And as we go to the right, the graph goes up to positive infinity. It is continuous on the interval 0 to infinity. And it's increasing from 0 to infinity. Pause the video and try B. Again, hopefully you got these same answers. One thing I want to point out, I had put a bracket there, but really it's increasing exclusively from 0 to infinity, not including 0. So that should be a parenthesis. When we're talking about increasing, decreasing intervals, we should always be using our parentheses. With a power regression, we can actually take a table full of data, build a power model, and then use that model to predict future values. So you can see right here, it goes through and gives you all the buttons that you could push for your TI calculator. Over here on the left, I'm going to show you what this would look like using our Desmos calculator, because you can also use that as well. So a power function that we're trying to get it to write would be in the generic form, it would be y equals ax to the b. That's a power function. So that's what we're going to be using in Desmos. We need to know that function because it says power regression. So that's a standard power regression. Just like a standard linear regression, I'm going to write that at the top here. Linear would be y equals mx plus b. And a quadratic regression would be y equals ax squared plus bx plus c. These are just generic forms, okay? So in order to do this, we want to actually type in this table into our Desmos. So I'm going to press the plus button, and I'm going to say table. And then I'm going to start to type all of these values, all of the x values, 10, 20, 30, 40, 50, 60, 70. Next, I need to go back up here. When x is 10, y is 4.2, 16.7, 37.6, 66.9, 104.5, 150.5, and finally 204.9. Okay, you can see if I move this out, you can see the points. So now we just need to build a model that's going to connect those points, and then we can use that model to predict. So we already created the scatter plot. Done. Now we want to determine a power function to model this data. So in Y2, or the second spot, I'm going to type that expression. Y equals A x to the b. Now, it doesn't do what I want it to do there, and I get this exclamation point because there's too many variables happening. What we really need to do is reference this table right here. Notice this table is x1, y1. So right here, I can't just say y, I need to say y sub 1. Now, a way to do that is to press this button, or you can press Shift minus on your keyboard and it'll make a subscript. Shift minus makes a subscript. All right. And so now we're getting closer, but it's still upset with us because it's impossible to fit one function exactly through those points. We can get close though. So the last thing we need to do here, instead of it being an equal sign, we need to actually change this to an approximation. So we're going to take that back and change it to approximate. The way I did that, I pressed Shift and the button on my computer that was right next to the number 1, but I could have also pressed this button here. And now you can see it tells me my equation. It says y equals 0.04 x to the 2.00076. That is a function that if it doesn't go through the points, it kind of looks like it does, but if it doesn't go exactly through, it comes close. So let's copy this function down. Y equals 0.0417. I'm just going to round to 4 decimal places. X to the 2.00076. Now we're going to predict the braking distance of a car going 80 miles per hour. 80 miles per hour is a speed, so they're telling me an x value. So I can type into my calculator 0.0417 80 to the 2.0